Hello everybody. In this video, we're going to take everything that we've learned in the last couple of videos and we're going to bring it all together. And we're going to learn how to graph the equation or curve sketching. Curve sketching, and we're going to use calculus in order to graph seemingly complex equations with relative accuracy. So let's graph the equation, the function f of x equals x over x squared plus 1. Okay, so let's draw our axes. So our y-axis, so our x-axis. Okay. Okay. So is our y-axis or x-axis? Just label that real quickly. Okay, so first, let's find out if this graph intersects the x-axis. Does it have any zeros? Okay, so we can check that by setting this equal to 0, and we get 1, 0 at x equals 0. Okay, and that 0 occurs at 0, 0. Okay. So I'm going to make some preliminary markings. 1, 2, 3, negative 1. 1, 2, 3. 1, 2, 3. Okay, good enough. So now let's find out about any asymptotes. Let's check for vertical asymptotes. So we need to see where the function is undefined. Okay, now it turns out to be undefined, you need x squared plus 1 equals 0. But there are no real solutions to that equation. So there are no vertical asymptotes. Let's check for horizontal asymptotes. To do that, we need to set the limit as x approaches infinity of f of x. Okay? And just by looking at the equation, you can see that because x is raised to a higher power, the denominator, it will go towards 0 a lot faster. And as x approaches infinity, you'll get much closer to 0. So the limit as x approaches infinity will be 0. Okay? So we have a horizontal asymptote at x equals 0. Sorry, y equals 0. So we have a horizontal asymptote at y equals 0. So now let's get to the calculus. Okay, we're going to try to find any extrema and where the function increases and decreases. So let's find f prime of x. F prime of x, well, we can use the product rule. Sorry, the quotient rule. Okay, so we have f prime, so 1 times g minus g primes 2x f. All that over g squared. Okay. So we get x squared plus 1 minus 2x squared. So you have 1 minus x squared over x squared plus 1 squared. So if we set this equal to 0, well, or undefined, we can find critical points. Now, we know that this function is never undefined because the denominator can never equal 0. So we not only need to set the numerator equal to 0 so we can find any critical numbers, because that is when the derivative equals 0. So if I set up my number line, we can see that the derivative equals 0 at x equals negative 1 and x equals 1. So at we're going to have to check values to see where, on which of these intervals is the derivative positive or negative. Okay, so at x equals 0, f prime of 0 is 1 minus 0 squared. So that's just 1 over 1 squared. So that's 1. So we know for a fact that this is positive. Now, let's do a value negative 2. Okay, select integer values. 1 minus negative 2 squared, that's 1 minus 4. Well, 1 minus 4 is equal to negative 3. Okay? And because the denominator is always positive, this is negative. We could say the exact same thing by using 2. So we get minus over here. So we have extrema at negative 1 and 1. Negative 1 will be a relative minimum. We negative 1, comma. Well, if we find f of negative 1, we get negative 1 over 1, because 1 is negative 1 squared, plus 1. So negative 1/2. So let's place that there. So this is one of our points. And our relative max will be 1, 1/2. Okay? Now let's find some inflection points and look at the concavity of the function. Now the function that we have f prime of x is kind of hard to take the derivative of, but we can do it. So f prime prime of x will be a derivative of f prime of x. So f prime of x will be f prime, negative 2x, g. So let's just expand g, so the denominator. So that's x squared plus, well, x to the 4th plus 2x squared plus 1. So x to the 4th plus 2x squared plus 1. Yes? Minus g prime. Well, we could use the chain rule for this one. Okay? So we have 2x times 2 times x squared plus 1 times 1 minus x squared. We could have easily just taken the derivative using the power rule over x squared plus 1 to the 4th. We won't have to worry about that. Okay, so if we simplify this, we get negative 2x to the 5th minus 4x to the 3rd minus 2x. So this is minus 4x times x squared plus 1, 1 minus x squared. Okay, so this is 1 plus x squared, 1 minus x squared. This is a difference of 2 squares, so this is just 1 minus x to the 4th. Right? So we have negative 4x times 1 minus x to the 4th. So we have 4x to the 5th So we have 4x times 1 minus x to the 4th. So 4x times 1 is 4x minus, well, plus, minus 4x to the 5th. Sorry, it's a little confusing with the signs there. Now, solving this equation, you get 2x to the 5th, right? Negative 4x cubed, well, that's still there, minus 6x. Now we can solve this equation. It's going to be a tough one to solve, but we can factor out 2x. Factor out 2x, we get 2x times x to the fourth minus 2x squared, yes, minus 3x, minus 3. Okay, so we can factor this. Okay, the 2x, I think we can factor this because 1 and negative 3. Yes, we can factor this. We can factor this into x squared plus 1 and x squared minus 3. Good. So we have x squared plus 1, x squared minus 3, and we just set that equal to 0. See, the second derivative one is always pretty much harder. So x squared plus 1 does not have a solution. So we only have to consider there are 3 possible points of inflection. X equals 0, x equals, well, positive root 3. But you can't forget the negative root, so you have negative root 3 as well. Okay? So now we have to check, okay, the concavity. So, well, negative root 3 is about, root 3 is about 1.732. So let's just check negative 2 first, okay? So negative 2, that'll make it negative, positive, and negative 2 squared is 4 minus 3 is 1. So we have negative, positive, positive. That will make it negative. So it's concave, should be concave down, okay? Now from negative root 3 to 0, let's try 1, okay? Negative 1. So 2 times negative 1 is negative. We have a positive from the middle term, it's always positive. And we have a negative. So we have 2 negatives and 1 positive. That will make it a positive. It's concave up from that in that interval. So what about from 1? So we have positive, positive, but we have a negative again over here. So this, it will be concave downward from 0 to root 3. Now, from root 3 to infinity, let's check 2. So we have positive, positive, positive. So it'll be concave upward. So all we need to do is graph the inflection points. Okay? So we have inflection points. It's getting a little messy, but at x equals 0, x equals plus and minus root 3. So x equals 0, we already have that. In fact, let's label it. And now we have root 3 over root 3 squared plus 1. Root 3 squared is 3 plus 1 is 4. So we have root 3, I would bet is around here, and I could sort of estimate is over here. Okay? So this is my estimate, root 3, negative root 3, and this is negative root 3 over 4. You can do the same thing over here. You can sort of estimate that this is positive root 3 over 4. And now we can construct a graph. Okay, so it's concave downward from here to negative root 3, but it's approaching y equals 0. So we can draw this to be sort of concave downward. This is an inflection point, so it becomes concave upward, but still decreasing. So let's start to flatten out the graph until it hits this minimum point, at which it's still concave upward. So we're gonna make it curve up until it hits 0. At 0, we see it's concave downward. Concave downward. So we start to flatten out and form like a frown until it hits this maximum point, okay? at 1 comma 1/2, where there it starts decreasing till it reaches this inflection point. This inflection point tells us it's going to be concave up till infinity. So we start to flatten out and start to approach 0. That's it. We just sketched the graph of x over x squared plus 1. It's sort of exhausting, but it's very satisfying once you're done. If you have any questions, comment down below and I'll get to you as soon as possible. Thanks for watching.